This is our video 6 on fluid mechanics, and it mostly will be on more practice questions, and I think we may have another 1 or 2 more videos where we do just practice questions. So let's look at some of the first questions. Air trapped above liquid ethanol alcohol in a rigid container. If the air pressure above the liquid is 1.1 atmospheric pressure, determine the pressure inside a bubble 4 meters below the surface of the liquid. Density of ethanol alcohol is 806 kilogram per meter cubic, and density of air is 1.29 kilogram meter cubic. So in order for this bubble to stay bubble, it has to match the pressure outside. So, and the pressure outside is going to be so the pressure outside is going to be the atmospheric pressure plus the rho GH underneath the liquid ethanol alcohol. So the pressure is going to be 1.1 atmospheric, which is 10 to the 5th, plus rho, which is 806 G, and H is height 4 meters. So the pressure is going to be equal to 142, 240 Pascal. So 142,240 Pascal. In this question, they say that Blaise Pascal duplicated Torricelli's barometer using a red Bordeaux wine of density 984 kilogram per meter cubic as the working liquid. What was the height H of the wine column for normal atmospheric pressure? Would you expect the vacuum above the column to be as good as for the mercury? So the density of the mercury is 13.6 kilogram per meter cubic. So I drew the picture for you to show the pressures around that, the way it changes. So the pressure, it is in equilibrium. So that means this pressure, P sub 0, the atmospheric pressure, is equal to that pressure. And this pressure with the water in the container is the same everywhere. So it's the same pressure right here, and it's the same pressure right here. So I can say that the pressure in the wine is equal to the atmospheric pressure. And that means rho GH is equal to 1 atmospheric pressure. That means that 984 times 10 times H is equal to 10 to the 5th. So H is equal to 10.16 meters. So 10.16 meters. What if they used mercury? So if I used mercury for the same calculations, I will have the pressure of mercury, which is the density of mercury, which is 13,600 times 10 and times H, and equals 10 to the 5th. Then H in this case would be equal to 0.735 meters. So there's a huge difference between 10 meters and 73 centimeters. So that's probably the reason why they choose to use mercury to determine the pressure change in atmospheric pressure change instead of anything else. So mercury is commonly used in barometers because it has high density. That means the height of the column can be reasonable size to measure the atmospheric pressure change. And the barometer is used, water, for instance, would need, like we see in this picture, we had for wine, it would be 10.16 meters, but let's say if I used water, that would be 16 that would be 13 times taller than if I use mercury barometer to obtain the same pressure difference. In this question, they say a 10 kilogram block of metal is suspended from the scale and immersed in water. The dimensions of the block are 12 by 10 and by 10 centimeters. The 12 centimeter dimension is vertical, and the top of the block is 5 centimeters below the surface of the water. What are the forces exerted by the water on the top and the bottom of the block? And take the atmospheric pressure equals to 1.01 10 to the 5th Newton per meter squared. At first, I'm going to calculate the area on the top and the bottom. So 12 centimeters is the height of the block. Then the area of the bottom and the top is 10 by 10 centimeters. So that gives me 100, 10 to the negative 4 meters squared. So it's 0.1 times 0.1. So there's different pressure between the top and the bottom of the block. And the pressure on the top is going to be equal to the atmospheric pressure plus rho GH, which is 5 centimeters below the surface of the water. So they say 5 centimeters below the surface of the water. So that gives me 101,300 plus the density of the water is 1000 times G and times H 0.05. That will be equal to 101,800 Pascal. The same we will do for the bottom. So the pressure at the bottom is equal to, again, atmospheric pressure plus rho G. In this case, different H, it's 12 centimeters plus the 5 centimeters above the water, or below the water. So we have 101 and plus rho, the water, density of the water, G. And H is 17 centimeters. It's 12 centimeters the height of the block and plus 5 centimeters below the water at the top of the block. So that's 0.17. And that will give me pressure at the bottom equal to 103,000 Pascal. And because the pressure is equal to the force over the area, I can calculate the force at top is equal to pressure times the area, that's 101,800 times the area, so it's 0.01. That gives me 1018 newtons, the force on the top. And the force at the bottom is 103,000 times the area, which is 1030 newtons. The difference between these two forces is going to be the buoyancy. So the buoyancy is actually equal to 12 newtons. And so this is the buoyancy, 12 newtons. And because the mass of the block is 10 kilogram and the buoyancy or the weight of the block is 100 newtons and the buoyancy force, so down we have the force pulling with 100 newtons, but buoyancy is 12 newtons, then the reading on the spring scale is going to be, so let's do the tension, or the reading on the spring scale is going to be 100, the weight of the block, minus 12, the buoyancy force, which gives me 88 newtons. And for the last question, they ask you to show that the buoyant force equals the difference between the forces at the top and the bottom of the block. So I just did the difference between the forces at the top and the bottom. So I'm just gonna show what the buoyant force is equal to. And the buoyant force, if I just did the buoyant force calculations, is equal to the weight displaced by the water. So the weight is the mass of the water that the block pushes up times the g, and the mass of the water is the density of the water times the volume of the block times g. So the buoyant force should be equal to, if we calculate, to 12 newtons. So we have the density of the water. The block volume is 1210 to the negative 6, because it's 90 times 90 times centimeters, and times 10. So I have 1, 2, 3, 4, 5, 6 zeros. That cancels our negative 6, and that will gives me 12 newtons. So that proves that the difference of the forces on the top and the bottom of the block is actually representing the buoyant force. In this question, they say a light spring of force constant K 160 Newton per meter rests vertically on the bottom of the large beaker of water. A 5 kilogram block of wood, density 650 kilogram meter cubic, is connected to the spring, and the block spring system is allowed to come to static equilibrium. What is elongation delta L of the spring? So let's write the forces that are acting on the block. We have the force of gravity, we have the force of the spring, and we have the buoyancy force. And it is in static equilibrium. So the forces that we have, upward force is, the net force is equal to 0, equilibrium. So the upward force is buoyancy minus mg, and minus the force of the spring, and that is equal to 0. So the force of the spring is going to be equal to the K and delta L, and equals to, if I solve the top equation, it equals to the buoyancy minus mg. So now we have K delta L is equal to, the buoyancy is the density of the water, it's the mass of the water, the volume of the block times g, minus the mass of the block times g. And they tell me the mass of the block and the density of the block, so I can calculate the volume of the block. So if I know the density is equal to how much mass per volume, I can calculate the volume of the block is equal to the mass of the block, 5 kilograms, divided by the density of the block, 650. So the volume of the block is equal to 7.7 10 to the negative third meter cubic. So I have the volume of the block, and now I can plug it in instead of the volume of the block in my equation. So now if I calculate delta L, the one that they asked me to find, delta L is equal to the density of the water times the volume of the block times G, minus the weight of the block itself. M is 5 kilogram and G is 10, so that's minus 50. And all of it divided by K, if I solve for delta L, so that's 160. And then delta L is equal to 0.169 meters, or 16.9 centimeters. In this question, they say that inside diameter of the larger portion of the horizontal pipe is 2.5 centimeters. Water flows to the right at the rate of 1.8 10 to the negative 4 meter cubic per second. determine the inside diameter of the constriction. So they give me the volume per second rate. The volume per time is equal to 1.8 10 to the negative 4 meter cubic per second. That is the same as the volume, which is area, times the distance over the time, and distance over time is the velocity. So the volume per time is equal to the area times the velocity. So from here I can find the velocity at so I'm going to call this part is 1. Velocity of 1 is equal to the flow rate, which is 1.8 10 to the negative 4 divided by the area, and they give you the diameters. The inside diameters of the larger portions are given 2.5 centimeters. So I have pi and r, which is 1/2 of 2.5 centimeters, so that's 1.25 centimeters squared. And that will give me the velocity of 0.367 meters per second. The differences in pressures in 1 and 2 regions, so the change of the pressure between 1 and 2 is going to be the difference of their heights. So it's going to be rho g, and then I have the h1 minus h2. So the pressure in 1 is larger than the pressure in 2. And that will give me, it's the water, so that's rho g, and the h is 5 centimeters, the difference between them, so that's 5 10 to the negative 2, and that will give me 500 Pascal. Now I can use Pascal's principle to calculate the velocity in the second area. So I'm going to have Bernoulli's equation, which is P1 plus 1/2 rho V1 squared in the first region plus 1 rho GH at the top of the first tube, so that's 1, and equals to P2 plus 1/2 rho V2 squared plus rho GH2. Now P1 minus P2 is delta P, so P1 minus P2 is the same as delta P. So I can write delta P equals 2. And I'm going to move everything to the other side and factor out. So I have 1/2 rho, and then V2 squared minus V1 squared. And then I have plus rho G, and then I have H2 minus H1. If I plug in my numbers, I have delta P is 500 Pascal, then 1/2 of 1000, because the density of water is 1000, gives me 500. Then I have V2 is the velocity I'm looking for, squared minus V1, and I just calculated V1 earlier, so that's 0.367 squared, plus rho times G, that's 10 to the 4th, or 10,000, and then H2 minus H1, so 5 centimeters minus 10 centimeters, will give me negative 0.05. Now if I do my calculations, I will get V2 is equal to 1.06 meters per second, and I can use the earlier equation to calculate the area 2. So area 2 is going to be equal to the rate of flow, and the rate of flow is the same, it doesn't change no matter where you look in the pipe, and that is 1.8 10 to the negative 4. That's the number that they give us, 1.8 10 to the negative 4, and that is divided by the velocity, which is 106, and that will give me 1.71 10 to the negative 4 meter squared. So that is my area 2. And they ask you to find the diameter. So the area 2 is equal to pi r2 squared. So r2 is equal to 0.74 10 to the negative 2 meters, and diameter is twice as big. So the diameter that they ask you to find, the diameter of 2 of, so that was the question, determine the inside diameter, is twice this much. So that will be 148 10 to the negative 2 meters. In the next question, they are saying that 1 kilogram beaker containing 2 kilogram of oil and density is given. Rest on the scale. A 2 kilogram block of iron and the density is given is suspended from a spring scale and is completely submerged in the oil. Find the equilibrium reading for both scales. So before the block of iron put inside, the bottom beaker, so I'm gonna say the weight at the bottom, was equal to the weight of the beaker, which is 10 mg, plus the oil, which is 22 times 10 mg. So that was 30 newtons. And that was before the block was put inside. And then after the block was put inside, well, actually, let's do the weight of the top reading is just the block itself, and the block is also 2 kilogram block, so the reading was 20 newtons, and that was also before the block was put inside of the oil. Then the top reading is gonna be less after the block was put inside of the oil by the buoyancy, so the top after will be reading the mass of the weight of the block minus the buoyancy force. So that is 20 minus the weight of the water that the block displaces, which is density of the weight of the oil. So that's the density of oil, which is 916, times the volume of the block. So we need to find the volume of the block. So I found the volume of the block on the side. So it's the mass divided by the density of the block. So then I plug in 25.4 10 to the negative 5 and times G. So it's the mass of the oil displaced times G. So the top reading is going to be equal to 20 minus 2.3, which the buoyancy is 2.3, which gives me 17.7 newtons. So that's the reading of the top after the block was put in oil. And then because the buoyancy force acting on the block is 2.3, that means the bottom is gonna now be different as well. So the weight at the bottom, that will show the scale at the bottom, will also show me not 30 newtons as before, but the amount of buoyancy force that is pushing back against the bottom weight, 2.3. So that's going to be, at the bottom reading is going to be 32.3 newtons. So that's the bottom reading after the block was put inside of the oil. And I will stop this video at this point. So this was our fluid mechanics 6 video with some more practice on fluid mechanics problems. And thank you for watching this video. I will see you in the next one.